So, we are discussing time resolved fluorescence upconversion technique, and once again let me state that the slides are all from Shobhan Sen of JNU. So, this is where we had stopped in the previous module, and what we have here is we have a schematic of the optics that are there in upconversion. Now, we want to use some animation to show you how the decay is actually recorded. Now, before that, let us just quickly remind ourselves what we have. You have a titanium sapphire laser. Right now, you do not have to worry about anything else, but typically we have a 100 femtosecond pulse. We have 100 femtosecond pulses at 80 megahertz. Then this is directed into the spectrometer. This is the part that we had discussed earlier, the spectrometer. A lens L1 focuses the red light onto the second harmonic generation crystal, and the second harmonic generation crystal that is used is typically a BBO crystal. What is BBO? Beta barium borate. That is usually the nonlinear optical material that is used everywhere now. Then what this one does is that it converts some of the red light into blue light. Both are collected by this lens. So, see, the thing is, in order to get best result, you have to focus your light, but then the output of that is a diverging beam. You cannot work with a diverging beam, you want to collimate it once again. So, this combination of two lenses, one focusing lens and one collecting lens, is ubiquitous in when you work with optical instruments. Why do we need to focus? Because let me write now, rather let me draw. What we had discussed in the previous module, without drawing anything, I think it is better to draw, otherwise it may not be very simple to visualize, is that we said, let us say this is the ground state of your BBO or whatever it is. So, first you have this first photon coming, and it is omega 1, in keeping with the terminology we have used later. It causes a promotion, and usually the promotion is not to a stationary state, it is to a virtual state. We have discussed that already. For second harmonic generation, you require the presence of another photon omega 1, which promotes the system to another virtual state. And then, as we said, there is no memory. When the system is here, it does not remember whether it came there by 1 step or 500 steps. So, the light that comes out is like this, 2 omega. This is second harmonic generation, put very simply for you. Now, for this to happen, what is the requirement? The requirement is that when you promote up to here, another photon must be there, and when I say there, I might clarify a little bit, saying the second photon must be there and must be there at that instant. Let us say this is the cross section of your crystal, and let us say you have promoted to this virtual state at this spot. It makes no sense if you have another omega 1 available here, it has to be here, and it makes no sense if the second omega 1 comes 2 years after the first one. Well, 2 years of course is an exaggeration, it must be there at that instant. That is why, first of all, you have to focus using the optics that we have shown earlier, so that you have a lot of photons here, and when you use a pulse, this is the typical shape of a pulse, intensity versus time, all the energy is packed in this short time. So, within this 100 femtoseconds, you can expect that there will be a large number of photons that will be there to serve as a second omega 1, right. That is why it is convenient to get second harmonic generation if your laser is pulsed. Okay. So, this is why we need to focus as well. Okay. Now, let us return to our presentation. So, this lens collects it straight. This is a dichroic mirror, DM means dichroic mirror. Blue light is sent in this side, and if your alignment is perfect, then it goes as a collimated beam. it goes to some other optics. We have discussed neutral density filter, which is ND. What this is, we will come to this in this module or the next. Then you have M5, which is actually another dichroic mirror. Residual red goes this way, blue light goes here. Again you have a lens which focuses the light onto the sample. And one thing I forgot to say in the previous module is that if you are working with liquid sample, then you want to rotate it, so that the same point does not get illuminated always. And if it is a solid sample, then you want to translate it, and typically translation is like this. There is a name for this kind of a scanning. What is it called? It is called raster scanning, right. If you go like this, then the same spot is never hit by light twice. So, possibility of damage is minimized. So, once again we have this familiar focusing and collecting optics arrangement. Once again, if your alignment is perfect, then what comes out of this lens is a collimated beam, but in this collimated beam it is nothing, it is anything but monochromatic. You have blue light as well as fluorescence, and in fact blue light is more intense. That is why you use F2, which if you remember is the long pass filter, which cuts out the blue light, the excitation light, laser light, allows only fluorescence to go through. And then this lens focuses it onto the some frequency generation crystal. Here what happens is, on the other arm, red light, which is called gate light, omega 1 as we have put it, goes to this mirror M3, then to M4, hits the retroreflector, is turned back, and the retroreflector is actually mounted on a 1 foot long screw, which can be moved using a what is called a step motor. Step motor means something that does not turn continually, but goes in steps. So, if you step motors are quite common in day to day use, they are used in printers for example, and there are many other applications. So, from M6 it goes to M7, same lens is used to focus it onto the some frequency generation crystal. If everything is perfect, then you get omega 1 plus omega 2 some frequency, and then you detect this some frequency. Okay. And here when I say everything is perfect, what does it mean? One very important parameter, two parameters. One is that both the spots must have been focused, both the light beams must have been focused on the same spot, and you understand why. The diagram we drew a little while earlier, the two lights have to be spatially overlapped, otherwise they cannot combine. If one spot is here, one spot is here, how will they combine? Second thing that we have not discussed so far, because we are going to have a little more discussion when we talk formally about nonlinear optics, is that the phase angle of this crystal has to be right. So, basically some frequency is very strongly dependent on the angle of the crystal with respect to the incident light. It typically works in a very narrow range of orientation. So, what you do is, in order to get good some frequency generation or good second harmonic generation, you have to angle tune the crystal, turn the crystal until you get a good some frequency or good second harmonic light, okay, and you detect it. Now, we come back after 10 minutes of recapitulation of what we said in the previous module. We come back to the question we asked: what does all this have to do with femtosecond time resolution? Remember, we are doing this because you cannot have electronics that can do a real time femtosecond measurement. All electronic components have the response time, which makes them slow. A microsecond is something electronics can handle quite comfortably, not femtosecond. So, essentially we are trying to overcome this limitation of electronics by using something that is faster than anything else. If you leave out things like tachyon and human mind, what is the fastest thing you know of, especially as is a spectroscopy course? Light, right? Light. Since electronics is too slow, we have to use the fastest thing at our disposal, that is light, to get the resolution. Okay. And what I will do is, first of all, I will draw, and then we are going to show you an animation. So, let us go back to the drawing board. Okay, let me draw omega 1 in blue, sorry, omega 2 in blue and omega 1 in black, right. Now, if I want to plot intensity versus time for omega 1, what does it look like? Intensity versus time plot of omega 1, something like this. Yeah, it is a pulse with a finite width, 100 femtosecond or whatever. If I want to make the same plot for omega 2, what would it look like? Fluorescence decay, right. So, it would go up and come down, something like this. It can come down completely, it can be incomplete, whatever it is. Now, see, if you go back to the schematic of the instrument, what we have essentially is that, drawing it very simply, this is your omega 1. I am not drawing the bits of optics, I am just drawing the path. One thing I cannot avoid drawing is the some frequency generation crystal. What about omega 2? Omega 2, well, there is some path before this, and omega 2 also has some path before this, and then it comes straight. It would better overlap with omega 1 exactly at SFG, which it does not. So, what I will do is I will just make the SFG broader. In real life, I cannot do it, it would better fall on the same spot. Okay. Now, see, omega 1 has travelled some path, omega 2 has travelled some path, right. And if you remember, omega 1 retroreflector is mounted on a 1 foot long screw, which I said is operated by a step motor which can move forward and back. What does it mean? That means omega 1 has a variable path length, omega 2 has a fixed path length, and I can move omega 1 so that the path difference between omega and omega 2 can be altered, all right. Let us say the path difference is something like this. And this is at the crystal, right. At the some frequency generation crystal, the path length is such that this is the scenario. Remember, black is omega 1, blue one is omega 2. I will not write that anymore. Okay. Now, in this situation, do you think there will be any some frequency generation? Yeah, omega 1 has come too soon. Okay. Omega 2 is not even there. So, there will be nothing, right. So, if I now want to plot intensity of some frequency as a function of, I will write delta. What is delta? The path difference. What will the intensity be? 0. You might see where we are going, because we have done a very similar discussion when we talked primary, well, in a very hand waving manner, when we talked about pump probe spectroscopy earlier on. Okay. Same thing. Now, suppose I change the path length of omega 1 and it comes here. Path difference is smaller. Will I get any some frequency generation here? No. So, once again, some frequency intensity is 0. Now, suppose it has come here. Now, this is the best possible situation. Okay. So, what will happen to intensity of some frequency provided the angle is right? It will go up. So, it shoots up. Now, if I change the path length of omega 1 a little more and bring it here, then what will happen? Intensity of omega is same, intensity of omega 2 has fallen off exponentially or whatever, and intensity of omega 1 plus omega 2 intensity of some frequency, what will it be? It will be something like intensity of omega 1 multiplied by intensity of omega 2, and there can be some factor, something kappa. Okay. So, what we are doing here is that always intensity of omega 1 is constant, but intensity of omega 2 first of all is 0, then it rises sharply to some value and then it falls off. So, if you keep changing the path length, what will happen is intensity of some frequency will also change accordingly. So, if it comes here, even though intensity of omega 1 is the same, intensity of omega 2 is a little less, the fluorescence has decayed a little bit, it will come down accordingly. If you keep on changing the path length, then the intensity of some frequency will fall off, and it is important to understand that the shape of this curve is exactly the same as the shape of the decay of omega 2. So, what we have generated here is a map of the fluorescence decay. We have generated a map of the fluorescence decay, and here it is important to not get confused about one point. The way it works is that the screw moves, so the retroreflector moves, and as long as the retroreflector moves, no measurement is done. Then it stops at some particular position, delta 1. It stays there for some time, half a second, 1 second, 2 second, 5 second, whatever you set it to be. That is when the measurement is done, all right. So, two things, first is movement of the retroreflector, second is actual recording or intensity of intensity. They do not take place simultaneously. When one happens, the other does not. So, when we make a measurement actually, then everything else is fixed. Mirrors are not moving, delta 1 value is fixed. So, we are making essentially a steady state measurement, and we are integrating for 1 second, 2 second, 5 second, whatever. So, the good thing about this is that you do not need a fast detector. You can actually get off using relatively inexpensive simple detectors like a regular photomultiplier tube, which you would use in a steady state fluorescence measurement, because you are performing steady state measurements here, and that is the beauty of the technique. You are using what is at your disposal, the fastest thing at your disposal, that is light. Okay. Just by moving this retroreflector a little, you are giving different path difference, and that is what can give you femtosecond time resolution. Before coming to that, let us show you the animation. All right, this is your back to the projection once again. So, this is what it is, and remember what we are doing now is, this is the same diagram that I just drew. Red is omega 1 and green is omega 2. So, what you are doing essentially is that you are changing the delay like this, and therefore, the path differences are changing. Omega 1 samples different parts of the decay, and that is how the plot is generated. And it is important to understand that what you generate is the map of the fluorescence spectrum, and this is exactly why I do not try to use my presentation. I like to use Shobhan's, because it takes a lot of time to make animation like this, I think. But now, now that you have seen the nice presentation, it is important to go back to the chalkboard once again and see whether what I see makes any, what I say makes any sense or not. So, let us go back and do a little bit of calculation once again. Right. You told me light is the fastest thing that we have, right. What is the speed of light? 3 into 10 to the power 8 meters per second. What does this mean? The rule of thumb that I like to use is light travels 1 foot, approximately 1 foot in 1 nanosecond. Okay. So, that is what it means. How much does the translation stage have to move if I want to give a if I want to change the path length, a path difference by 1 femtosecond? It is very simple. Let us say, so this is your retroreflector, right? This is omega 1. I am saying that I move it to this position, right, and there I am going to neglect this part, of course. The only thing that matters is this length. So, suppose I move it by delta, or rather let us say I move it by s, s is better, right. In class 9, 10 physics also we say distance is s. So, I move it by a distance s. What is the change in path length? Well, what is the change in time involved? If I move it by s, by how much more distance is light moving? S while going, s while coming. So, 2s, 30 centimeter is equivalent to 10 to the power 9 second, is equal to how many femtoseconds is that? 10 to the power minus 9 seconds, 10 to the power 6 femtosecond. Okay. How many micrometers is centimeter? 10 to the power 4, right? 4. So, 30 into 10 to the power 4 micrometer is equivalent to 10 to the power 6 femtoseconds. So, if I want 1 femtosecond, that will be equivalent to 3 into 10 to the power 5 divided by 10 to the power 6 micrometer, and that is equal to 2s. So, from here you can see what it will be. It will be something like 1 micrometer or something like that. So, basically you must have the precision of moving this retroreflector by a micron. Is it possible? It is possible, because you use a screw. It is very easy to get a pitch of less than a millimeter, and it is not difficult to move it by a fraction of a degree. That way you can get femtosecond resolution. So, this is how femtosecond time resolution comes. Okay. So, what do you need? You need to have a suitable pitch of the screw, and you need to have a step motor that is sufficiently accurate. Okay. It should be able to move in millidegrees or something like that. That is not very difficult to get. So, this is how you can get the femtosecond time resolution. Okay. This we have already answered, and I think now you have understood how we get time resolution here. We get time resolution because we can move this retroreflector in very small steps. So, we can actually give very small differences in path length, and then we make a steady state measurement. Now, you might remember that I told you that we use lenses to focus, but there is a better way of doing it. And the reason why I said it is that, again we are going to elaborate upon this point in one of the later modules. When ultra short light pulses go through any dispersing medium, they get broadened, and in fact it is used to our advantage in some application later on. But then if you want to make a measurement with a very good time resolution, your laser pulse and everything else must be very, very short. So, then you cannot use any optics through which the light goes. You have to use all reflective optics. In that case, what you do is, in fact, even here to focus the light on second harmonic generation, you want to use instead of a lens, you want to use a curved mirror, and then actually even this is not correct. You do not want to use a lens here. You replace all the lenses by parabolic mirrors like these. That gives you better time resolution. Typically in our instrument, we have 100 femtosecond pulse coming out of the laser, but when we measure instrument response function, it is no longer 100 femtosecond, it is close to 300 femtosecond. So, if you do not want that, if you want that your suppose you want to use a 50 femtosecond pulse, and you want your instrument response function to be no more than say 70 femtosecond, then you want to use all reflective optics like this. In fact, initially everybody made all reflective optics. They did not use lens for the fear of losing out on resolution. The problem here is that to get the first signal, if you build your instrument and you do it with parabolic mirror, getting the first signal is a complete nightmare. It is much easier to use a lens, because with the lens you have only one control, you have to move it forward or backward, and you already know what the focal length is. So, you already know the approximate position. It is much easier to get the first signal when you set up the instrument using a lens. That is why usually people are happy sacrificing some of the time resolution by using a lens, because that would give better collection efficiency, right. Now, this is an example of upconversion data. You can see this is the data and this is a fitting curve. We talked about fitting curve in the previous module, and you might be able to recognize here that the data quality here is definitely not as good as what we get in TCSPC. TCSPC gives unparalleled data quality, that is why it is so popular worldwide. But then if you want better time, then you have to use something like upconversion. You can also use something else called stick camera, we will talk about it in very brief. Next point of discussion is, why do you want to take care of polarization, and what are the things that can go wrong in an upconversion measurement. That is what we will take up in the next module.